Mhm. Okay, hello everybody. Today it's my pleasure to invite Professor Mikhail Zubkov from Ariel University to present his talk, Wigner-Weyl calculus and the theory of topological response. Misha, please.
Okay. So thank you for the invitation. I will be happy to share with you um, this stuff. This is a kind of a review talk. I will actually review the work which has been done here in Ariel since I'm here. And basically the subject is in between several branches of science, between mathematics and physics. Something, just a second. Okay. Yeah. So we have here on this side, on the side of mathematics, Wigner-Weyl calculus, which is close somehow to differential quantization. We have algebraic topology on this side, or in some sense, non-commutative geometry. On the side of physics, we have high energy physics. Basically, we're considering in this respect quark matter. And we have condensed matter physics, basically solids, two-dimensional materials, and also three-dimensional materials, which are called Weyl and Dirac semimetals, and also the superfluids, in particular helium-3a superfluid. And in the middle, what is called non-dissipative transport phenomena. In fact, these phenomena, they exist in these two branches, and they are described by topological invariance. And I'm going to discuss how this happens. Okay. This is a list of my collaborators, former and present, with their affiliations, present affiliations. And this is a basic list of papers, which I'm going to try to review. This is not a complete list. We have a bit more papers, but these are the crucial ones. And what we are speaking about? We are speaking about the, again, non-dissipative transport. And this non-dissipative transport, the examples of this transport phenomena like quantum Hall effect, chiral magnetic effect, chiral separation effect, chiral vortical effect, and some others. Actually, this effect is appearance of current. It may be electric current, axial current, energy current, and so on that flows without dissipation. There is a conjecture which is not yet proven for all possible non-dissipative transport effects. The conjecture says that the conductivities of all these transport phenomena are given by topological invariance. And actually, what I'm going to do, I'm going to show that indeed in some cases we have really topological invariance, and we will be discussing a bit this invariance. Where in physics we do see this? We see this in quark matter. And here you see the phase diagram of quark matter in the plane chemical potential and temperature. We have here the phase transition line. This is a chemical potential. This is a temperature. Our world, I would say, it is here at zero temperature and at zero quark potential. For chemical potential, when it grows, we enter here in this region, we enter the nucleus. And when the temperature grows, we pass something like phase transition, and above this transition, these are accelerators. I show the accelerators where the quark matter in this state may be achieved. So this guy is LHC, well known. This is a Russian accelerator. This is in Germany. This is in the United States. This I don't remember where. Actually here, about this phase transition, we have what is called quark-gluon plasma phase. And here we have the unknown region. For some reasons, it is not possible to study this this place of phase diagram using analytical and also numerical methods. At very large chemical potentials, most likely there will be the so-called polar superconductivity. But here, the situation is unknown. And there is a possibility that the chiral symmetry is restored here. And this is a place which is very interesting particularly for my research, because our results are the only precise results that can be applied to this place of phase diagram. While here we can do some analytical and numerical calculations. Here we can do some analytical calculations. In this region, it is absolutely impossible. And only our method, it allows to get some precise results in this space of phase diagram. Conductivities of some transport phenomena, they are expressed through topological invariance, and that's why we can get precise results here. I will discuss it a bit later, maybe. On the side of condensed matter physics, we have two-dimensional materials. And basically, in two-dimensional materials, we study quantum Hall effects. We have three-dimensional materials, which are called three-dimensional Weyl semimetals. And here we see chiral separation effect, chiral magnetic effect, and quantum Hall effect. What is quantum Hall effect? Is electric current orthogonal to electric field. Is quantum Hall effect. Chiral separation effect appears of axial current in the presence of magnetic field. Axial current directed along magnetic field. Chiral vortical effect, appearance of axial current in the presence of rotation. The direction of chiral axial current in this case is along the axis of rotation. Chiral magnetic effect is appearance of vector current, say electric current, in the presence of magnetic field, and it is again directed along magnetic field. Chiral magnetic effect can appear in the so-called A phase of helium-3 superfluid. So these are the places where all this can be seen, theoretically and practically. Now let me go to discussions of all this, and since I have a lot of material, I will just tell what I can tell during 1 hour, and after that I will stop and then we'll go to conclusions. So I will start from reminding what is degree of mapping. Because I'm speaking about topology, what is relation between topology and physics. So I will start from the simplest topological issue, which is degree of mapping. If we consider the mapping from S1 to S1, let's say degree of mapping is how many times the circle winds around itself during this mapping. And it is described, this mapping, by the function, by this function q of z, which has this form. The circle is actually the circle with the constant radius, given by this formula. And the n is in fact the degree of mapping. But we also can express this degree using this formula through this function q directly. This is the simplest example, I would say, of topological invariant. Now let's proceed. So we go to the next slide, and then the next slide, there will be the similar situation with the mapping from S1 to UN. And we have actually almost the same formula, like this. Where of course this is multiplied by unity matrix. And the degree of mapping in this case is given by this formula. We should divide by n, large, and this is again n. Now let's consider a bit more complicated situation. which is the mapping from S3 to SUN that corresponds to pi3 of SUN, which is Z. And now we can express the degree of mapping that corresponds to the element of a fundamental group. We can express it this way, where Q is this mapping, and this guy is again integer. Now, why I'm presenting here these well-known results? In order to jump to physics and to show expression for the quantum Hall conductivity in two-dimensional materials. So again, we're here. Here is expression for Hall conductivity. Hall conductivity is given by the number n divided by 2 pi with natural units, with h bar equal to unity and e equal to unity. And this guy is topological invariant. We're speaking about the homogeneous systems without magnetic field, without interactions, without disorder. These systems are called in physics Chern insulators or two-dimensional topological insulators. And as you see, this is the same formula as in the previous slide. So that guy is a topological invariant. This expression of quantum Hall effect in terms of topological invariance has been proposed for the first time by Matsuyama in 1987. And later it was explored in many works by Volavik and collaborators and by some others. The important thing is that in the original form, this formula, it was obtained for the case when interactions between electrons are not taken into account. The question is, what is happening when we take into account interactions? It appears that actually the expression for the Hall conductivity is not changed. And we, in the presence of interactions, we come to the same formula. Now, instead of g of p, in non-interacting g of p, we should insert the interacting green function. The green function with corrections due to interactions taken into account. And this has been proven in this paper in complete way. And this proof, it repeats somehow the consideration of this old paper, which was written even before the very expression I'm considering for n was proposed. So it even didn't work with this expression. It particularly considers this work the two-dimensional electrodynamics, and they actually consider the so-called Chern-Simons action, the induced Chern-Simons action, and they proved using their technique that the coefficient in this two-dimensional electrodynamics in this induced Chern-Simons action is not renormalized by interactions due to exchange by photon. We somehow expanded their technique to prove that in any case for two-dimensional topological insulators, the Hall effect is still given by this formula with this topological invariant. I will say this is the first result which I want to announce in this review talk. Now let's proceed further. Okay. So now let's go to the case when the system is not homogeneous. For example, if there is an external magnetic field and maybe disorder, impurities, anything else. So whatever we want, any inhomogeneity which we want. In that case, it appears that the formula again is almost not changed. We still have the conductivity given by this guy, n divided by 2 pi. And this n now is very similar to the previous one, but now we should insert, instead of the green function, instead of a green function depending on one momentum, we insert the green function depending on P and X, which is actually Wigner transformed green function. In that case, the green function, because the system is non-homogeneous, it depends, its Wigner transform depends on both momentum and coordinate. Again, if we come back, what is the difference when we come back? Here in this expression, we have G depending only on P. This is because the system is homogeneous. Only P is the only argument of G. And now there are two arguments, P and X for G, for GW. And in between, we have the Weyl products, the well-known Weyl products. And this has been proposed in this work. So this is the second result. Also in this paper, it is worth mentioning that in this paper, we considered non-interacting systems. Further, we extended the result to interacting systems and proved that actually the result is not changed when we're considering interacting system, when interactions are taken into account perturbatively. This is important, because if they are considered non-perturbatively, then we will come to the fractional quantum Hall effect, which is another story. We also dealt with it, but I do not review this result here. Okay. So the main point about this is that when the system is changed smoothly, then the green function is not changed smoothly. I forgot to say that green function is G, and what is Q? It is star inverse with respect to G. So there's a solution of this equation. And when we change the system smoothly, the value of n is not changed smoothly. What does it mean? When we change smoothly the system, its whole conductivity is not changed at all. It is, I would say that it is a very well-known result, but not proven in any place except for our papers. I think so. At least nobody still showed me the proof of the universe. So I hope that the result that non-renormalization by interactions and the disorder of whole conductivity is given by us for the first time. I hope so. If not, I'm sorry, but I haven't heard about this. Again, we proceed. And this is the paper where we proved that in the presence of interactions, there is not the presence of perturbative interactions. There is no change of this formula. Okay, we proceed. And now a bit different interpretation of this result in a bit different notation. So actually, if we denote this integral with the trace as bold trace, then our n may be written in this way. And we also omit the symbol of star, and we also substitute q by g to the power of -1, which means inverse to g with respect to Weyl product. Next step, we come here, and we say that this guy, this n, actually it can be considered as pairing of the first Chern-Kohn class, which belongs to cyclic cohomology, with cyclic homology determined by the class tau3, which is associated with the co-cycle written here. What does it mean? That means, first of all, that in non-marginal cases, the values of n are integer. And this means also that our topological invariant responsible for quantum Hall effect is a particular case of Chern-Kohn character. Chern-Kohn character is a more general notion, but our case is just a particular case of that. In that sense, it will be very interesting to study from the mathematical side this quantity. in particular in order to calculate it, because we do not know how in practice to calculate this n in many situations. I personally know only one situation when it can be calculated analytically. Numerically, we can calculate it somehow, but analytically it is difficult. And I know only one case when the external magnetic field is constant and there is no disorder, when we can really calculate it analytically. So it would be interesting to consider more cases, I would say. And this is the task for the future. Now, okay, let me go further. And here is the general scheme of our consideration. So we consider quantum field theory. We use Wigner-Weyl calculus. I will show you how we do use it to establish a connection between topological invariance and response of non-dissipative currents to external fields. This is what happened for a quantum Hall effect, which I showed above. And I will discuss below some other effects depending on time. How much I will be able to discuss, it will depend on time. Okay. Now, let me discuss the formalism which we are using. Since we developed a new formalism that allows to deal with non-abelian gauge fields, I will discuss both non-abelian and abelian, covariant and non-covariant formalisms in one place to unify the picture. So here you see the two sides. On the left hand side, Wigner-Weyl calculus ordinary one. On the right hand side, the covariant one. And what we're considering? A quantum field theory described by this partition function. Integration over fermionic fields with some action, typical action, like this. This is just example, not the general case. It's just example. And we can, on the left-hand side, use just ordinary Dirac operator Q. On the right-hand side, we can generalize it somehow with the functions, depending on coordinates with the derivative, with any power of derivative. And we assume that the powers are finite, but in principle, it may be extended to the situation when this n goes to infinity. Technically, it is possible. Now, the green function, what is it? It is this q to the power of -1. We take this operator. Its inverse is the green function in non-interacting theory. And we are discussing the Euclidean space-time, which means that we made a weak rotation from t to tau. Tau is imaginary time. So we are in Euclidean space-time always. Okay. Now, on the side of ordinary Wigner-Weyl calculus, we define in continuum space, we define the Weyl symbol of operator in this way. On the side of covariant Wigner-Weyl calculus, we supplement this matrix element by the parallel transporters to make the result covariant. And we define the covariant Weyl symbol of operator in this way. This is our definition. We actually took it from the previous paper by some people. I do not show it here, but that paper, it dealt with abelian case, and we extended it to non-abelian case. Okay. And now again, the comparison of Moyle product. So Moyle product in the case on the side of ordinary Wigner-Weyl calculus can be written in this way: Moyle product of two functions. This is itself a function of x and p. It can be written through the integral like this. And we have here the formula a, b, Weyl symbol of the product of operators is equal to the Moyle product of the Weyl symbols of these two operators. On the side of covariant Wigner-Weyl calculus, the star product is denoted by big star. And it is similar to the above expression, but the difference is that we also insert the Wilson loop in these points, we insert also these functions y and x at this point, points of the Wilson loop. And this is for covariant Wigner-Weyl calculus. On the language of derivatives, the same thing. Again, we have here this relation that xw star yw is equal to xyw. So while symbol of also covariant while symbol of the product of two operators is given by the star product of the two while symbols. But now the star is a bit more complicated than in ordinary case. And this is very useful for consideration of non-abelian gauge theories, as I will show you below. On the language of derivatives, the Weyl product is given by this well-known formula with this delta. Here, derivative with the arrow pointing out to the left, acts to the left, acts on the A. Derivative with the right arrow acts on the right. On the side of covariant Wigner-Weyl calculus, expression is more complicated. And it is even difficult to recognize what is this in terms of derivatives. So it's more transparent to use the previous slide for the definition of Weyl product of the two while symbols on the side of covariant Wigner-Weyl calculus. Okay. Now let's come back again to the quantum field theory described by partition function with some action, with some Dirac operator, and we have for the green function, for the while symbol of a green function, that is for the Wigner transformed green function. We have on the left-hand side this equation, which is called Wigner-Weyl equation. On the right-hand side, we have the similar equation, but with the big star. Okay. Now I wrote almost the same. So this is Wigner-Weyl equation in ordinary Wigner-Weyl calculus. This is Wigner-Weyl equation in covariant Wigner-Weyl calculus. And here the definition of the while symbol of Q in the case when A is equal to 0. The while symbol of operator Q is actually given by the covariant while symbol of Dirac operator is given by ordinary while symbol of Dirac operator with external gauge field set to 0. This is very important property of covariant Wigner-Weyl calculus. It is easy to calculate the covariant while symbol of Dirac operator. It's not so for the green function, which is inverse to it. For the green function, we have a more complicated expression. Specifically, we can expand our result for the green function, which is inverse to Q, on both sides for ordinary green function, for ordinary formalism, for covariant formalism, and in both cases we can we will have this expression. When we expand in powers of covariant derivatives, then on the 0th level we will have G0, which is equal to star inverse with respect to Q. And we set A equal to 0 here to calculate G0. To calculate G2, we take this expression. And this is correct on both sides for ordinary Wigner-Weyl calculus and for covariant Wigner-Weyl calculus. So when we are considering response up to linear, we will be able to use only these two, G0 and G2, and G1 is equal to 0. in this case. G1 is trivial. This is the solution of Wigner-Weyl equation, also for covariant Wigner-Weyl calculus and for ordinary Wigner-Weyl calculus. And in fact, we use this to calculate the response of, say, abelian vector current and non-abelian vector current to external electric field, ordinary electric field, or non-abelian electric field. And in both cases, we have in two-dimensional, 2 + 1 dimensional case, we have the same formula with the coefficient given by this expression, which is, as you see, that formula for the Korn-Chen character of G. Again, let me remind what is quantum Hall effect. It is appearance of electric current directed orthogonally to applied external electric field. Our result is that both in the case of abelian and non-abelian external field, both in the case of abelian and non-abelian vector current, we have the same formula with conductivity proportional to this guy. Okay, now if we consider the axial current instead of sorry, what is this? Okay, we consider the axial current, and we consider instead of 2-dimensional, 2 + 1 dimensional system, the 3 + 1 dimensional system, which is 4-dimensional in Euclidean space. Then the answer for the response of axial current to chemical potential is given by this. This is external field strength. This is N3, which is topological invariant. I will show you in the next slide what is N3, what is the integral over sigma 0. And mu is chemical potential, ordinary chemical potential. In fact, sigma 0 is a surface that consists of two hyperplanes, P4 equal to plus and minus epsilon. There are some reservations concerning this formula related to the case when we are considering lattice model, but I do not want to enter into these details. This is already considered, and we explored this relation to lattice models. In lattice models, we need some additional conditions for this formula to be correct. It's better if I will not discuss this, because this will require time. I do not want to enter into these details. Okay, so let me proceed. And on the next slide, there will be, I show the actually the sigma 0, which enters this expression. So again, what is sigma 0? It is a surface, hypersurface consisting of two hyperplanes. One is just above 0, another is just below 0. What does it mean? 0, 0 in P4. P4 is a Matsubara frequency. The singularities of expressions standing inside the integral are situated between these two planes. It is always for P4 equal to 0. It can be achieved when we adjust what is called Fermi energy, always. The places of these crosses are singularities of expression standing inside the integral that was shown on the previous slide. And these singularities, they mark the positions of Fermi surface in momentum space. In case when the system is non-homogeneous, this Fermi surface, its position in momentum space depends on coordinates. That means that we speak of Fermi surface, coordinate-dependent Fermi surface. And this guy, this N3, is topological invariant as well. Again, with some reservations related to case when we would consider the lattice models. And this result has been given in this paper rather recently for the case of non-abelian external gauge field. And now we're actually discussing the so-called Carrel separation effect. Response of axial current, again, when we come back, we recognize that what we're considering is response of axial current to chemical potential. It is linear in external magnetic field. If F corresponds to external magnetic field, we are speaking about Carrel separation effect. And this quantity, which is standing here, is actually the conductivity of Carrel separation effect, both in the case of abelian and non-abelian gauge theory. Now let me go to the next issue. The next issue is related to the anomaly, Carrel anomaly. We're considering actually the, okay, this way. No, okay. We're considering the quantum field theory with a partition function given by this expression, with an operator Q, which has this form with zeros along the diagonal, with O and O cross out of diagonal, and this O is a pseudo-differential operator, I would say elliptic differential operator. We consider the zero modes of this O, difference between n plus and n minus, which is dim ker O minus dim ker O cross, is an algebraic index of operator O. It is related to what is called anomaly in quantum field theory, which is integrated anomaly, integral of trace of covariant derivative of current J. And it is given by 2I appears here, times difference between n plus and n minus. And this guy, it is related to the topological index of operator O, which is given by Chern class of an associated virtual bundle psi. It is associated with the operator O. In case when there is when the manifold is curved, we should add here also the Toda class, but we are considering the flat case, flat space. That's why the only part of on the right-hand side is related to the Chern class. So anomaly is equal by 2I times this topological index. This is a general consideration, which is very well known. Now let us consider the situation when we have external non-abelian gauge field A, and in addition we have an inhomogeneity of the system taken from the other source, not important from which one. Which is important here, that source of inhomogeneity does not lead to non-trivial topology. Say, if we would consider the curved space, then in general case there may be a topological invariant composed of the special curvature, gravitational curvature, and then we will have non-trivial Toda class. Now we do not consider this situation, and we also do not consider the situation when any other dependence on coordinates other than through the external non-abelian gauge field leads to non-trivial topology. So we would expect, but there is topology in momentum space. so we would expect that in this situation, the right-hand side of the Atiyah-Zinger theorem will be reduced to the product of the two things. The first thing is the Chern for gauge field, and the second thing is the Chern for momentum space topology. And this is really what we have proven in this situation. So our result is that we can represent the anomaly, which is up to the imaginary unity. It is topological index. Topological index is factorized into the product of n3 and the number of instantons. Number of instantons is the Chern for the gauge field. And this n3, it appears that it is the same n3 which we got for the chiral separation effect, for the conductivity of chiral separation effect. So how do we prove this? To do this, it can be done many ways, I suppose, but what we did, we used point splitting regularization. What does it mean, point splitting regularization? Actually, we're considering the action in this form. We have the psi bar, psi, and the q. And this S may be written as a trace of Q, product of Q and operator rho with a head, which matrix elements are given by the product of psi of X and psi of Y. So if we do not use any regularization, the answer is divergent. But we use regularization, and the point splitting regularization, what it does, it shifts this X to X minus epsilon, and it shifts this X to X plus epsilon, and it adds, to make everything covariant, it adds the parallel transporter corresponding to the gauge field. And then our regularized expression for action is this one. So this is okay. This is expression for S, and let us consider an inertial current, which would appear if the chiral symmetry is not an anomalous. We are considering the chiral transformation with alpha, which belongs to the algebra of gauge group, and psi bar transforms this way. We consider variation of our action, of our regularized action, and we come to expression that this variation is given by the product of alpha and gamma epsilon and the trace and an integral, and gamma epsilon is this guy. These big stars are those covariant Weyl products, covariant Moyl products. And this rho is given by exponent IP epsilon big star rho W big star exponent IP epsilon. This is actually like parallel transporter in momentum space. No, sorry, in X space. It shifts X by epsilon. And actually we can express gamma as covariant derivative of J, which is axial current. Now we call it axial current, this guy. And this axial current, we have the formula like this. Plus dots. Dots mean the higher orders in derivatives. Okay, with this we proceed. And again, the formula for gamma, which enters variation of action, it contains the axial current. Now we define the axial current in this way. And the Carrel anomaly is a trace of covariant derivative averaged covariant derivative of J. It can be expressed in this way. Now, if we would add here the integration of x on the both sides and use cyclic property of the covariant star, we will get right on the right hand side of this expression, we would get 0. The point is that we cannot do this because of divergences. With x integration over x, we actually have expression like 0 times infinity. Infinity comes from the infinite integration over x. That's why we need to regularize this expression. Actually, what we do not consider the integration of x at this stage. And we consider the right-hand side expansion in powers of epsilon, expansion of this expression in this form. We express it as sum of the terms. Each term has this form, times something, times some structure. And it appears that when epsilon goes to 0, epsilon goes to 0 means that we take off regularization. In fact, on the right-hand side, only the terms with the powers of epsilon equal to unity or 0 remain. In fact, there is no term with n equal to 0. There is only term with n equal to 1. All terms with n larger than unity are irrelevant at the limit epsilon goes to 0. So we keep the terms with n equal to 0, and we come to expression on the next slide. The expression like this. Expression like this. Next step, we use the theorem, which may be even read off from some textbooks, classical textbooks on quantum field theory, that this guy, if we average over interactions or over directions, sorry, when epsilon goes to 0, we recover integral of derivative of f. So we actually may substitute what is standing here by this guy, by this derivative. Instead of this, we will insert derivative. And here it is. The answer will be 0 if there are no singularities of expressions standing inside the derivative. But there are singularities. And because of these singularities, we will have non-zero answer. Now we express, now we made the important step. Important step is related to the requirement that which I announced in the beginning, that the topology in coordinate space is only due to external gauge field. What does it mean? When we remove gauge field from consideration, then the function qw of x and p is homotopic to a function q tilde of p only. There is no dependence on x in q tilde. qw of x and p is homotopic to q tilde of p. And q tilde of p is a solution of this equation. So we rewrite everything in terms of q tilde instead of q. And with this, we come to the next slide. And on the next slide, we will have expression for anomaly already written in this way. After the integration, after everything, after some steps which I omit here, but we come to expression for A, which is the product of imaginary number n3 and the number of instantons. Okay. So we come here and we get the result for chiral anomaly in terms of q tilde and g tilde. Here it is. As I announced already, the chiral anomaly or index of operator is factorized into the product of the two, N3 responsible for momentum space topology, and the number of instantons is actually corresponding to X space, coordinate space topology. But this is written still in terms of G tilde and Q tilde. It is not a regional green function, but we can come back to original green function and express it through original green function. Now with the stars. And now this, what is this? Is a Chern-Kohn character pairing with natural volume plus. So this is another result given in our paper recently, written recently, relatively recently. If we go to Minkowski spacetime, we will recover this expression with anomalies given by a real number, not imaginary one. Okay. If we restore expression for the topological index, we will see that what we did in practice, we calculated the topological index for the particular case when the only source of coordinate space topology is due to external non-abelian gauge field. So we have invariant in momentum space, let's say in momentum space, because we have here the star, which means that we have dependence on X. But anyway, this is like, let's say, momentum space topology times coordinate space topology contribution. And this is done in this paper, which we published only recently, this year. How much time do I have? I think that I do not have a lot of time already. I want to say that a similar result has been obtained before us 5 years ago by Piotr Surovko and collaborators. And when I announced this result in the conference in Portugal this year, he was very angry because I didn't mention his result. I really didn't know. So he actually got the same formula. I mean this formula, but this is what he did not get. His expression was written for N3. He did not call it N3, by the way. But anyway, this N3 in his notations, it was expressed through the Berry curvature in Berry curvature formalism, which is valid only for non-interacting theory. Advantage of our result is that the same result is the same result for N3 should be valid also in the presence of interactions. We just substitute Q and G by interacting versions of Q and G with all interactions taken into account. And this is what is not present in that paper by Piotr Surovko and others. But in principle, the line of thinking is very, very similar. And also, he did not use, he used other methods for the derivation of this result. Okay. Now let me consider the particular case. Of the system when N3 is non-trivial. Actually, in the case of ordinary quantum field theory, relativistic quantum field theory, N3 is just equal to the number of Dirac fermions. In the case of, in the general case, it may be any integer. And here I represent the simplest example of the situation when N3 is really not equal to unity for one Dirac fermion. This is when the operator O has this form. Pi is covariant momentum. Pi is actually equal to minus I derivative, like this. So in this case, we have N3 equal to this power N. Where do we see these operators? In condensed matter physics, these Dirac operators, they appear in certain solids. Really, they appear in certain solids in some situation. And that means that the application of this result, of our result, I would expect this application mostly in solid state physics. I think I do not have time already. I need to go already to conclusions. Before that, I want to briefly mention the other results which we got, which in my opinion are important. So the other results are related to lattice regularization of all this stuff. Lattice, actually, what I discussed before, literally, this is continuum field theory. But also, all this works on a lattice. And say Wigner-Weyl formalism on the lattice, it is very similar to Wigner-Weyl formalism in continuum, but technically it is much more difficult to work with this. And we proposed the two formalisms for dealing with lattice systems. In the simplest version of Wigner-Weyl formalism, our Weyl symbol of operator is given by this formula, which is just repeating the continuum formula. And the property of this formula on the lattice is that this identity, that the Weyl symbol of the product is equal to the Moyle product of the two Weyl symbols, is approximate. But it is so good approximation that in practice it can be used in any solids. What does it mean? In practice, when we are speaking about non-homogeneous systems, where non-homogeneity is due to external magnetic field, then for external magnetic field up to 10,000 Tesla, we can really use this formalism without any doubts. What does it mean, 10,000 Tesla? In real situations, in experiments, the maximum value of magnetic field, which can be achieved, is around 50 Tesla. So it can be used always. When we're speaking about lattice regularization quantum field theory, the situation is the same. So we can use this formalism, and in this formalism, everything which I told before is valid. Now the point is that also we derived the precise formalism for the case when we do not need this approximation. In this precise formalism was reported for rectangular lattice in this paper, for the honeycomb lattice in this paper, for finite rectangular lattice in this paper. And I cannot enter into details, but I can say that in these formalisms, precise Wigner-Weyl formalisms on the lattice, which is a separate mathematical issue, the expression A W cross B W is equal to A B W is exact, is precise, which is very useful for derivation of results for quantum Hall effect and so on. And this may also have application to solids, because in the solids there exist the so-called artificial magnetic fields. This is when we consider say layered systems with the layers slightly turned one with respect to another, then effectively the magnetic field, value of magnetic field when we need precise Wigner-Weyl calculus is reduced. It will be given by around that 50 Tesla or 20 Tesla or so on, effectively. But this is a separate issue, which I really do not have time to discuss. Okay, I think that my time is over. So I go to the conclusions. Let me go to the conclusions, which is at the end, at the very end. Oops, sorry. What does it mean? Okay. Again, slide. Sorry, I need to go to that. I have a lot of materials. Fortunately, I do not have time to discuss everything. Okay. Okay, these are my conclusions. So first of all, Wigner-Weyl calculus allows to represent in compact form the conductivities of several non-dissipative transport phenomena on uniform systems. And as I conjectured at the very beginning, these conductivities are expressed by topological invariance. And this is done for chiral separation effect, for quantum Hall effect. There is an issue of chiral magnetic effect, which I didn't discuss, unfortunately. We considered the non-abelian versions of quantum Hall effect and chiral separation effect. We obtained the expression for chiral anomaly, and in the considered case, it is factorized into the two topological invariants for momentum space topology and for coordinate topology given by instanton numbers. This is what I did not discuss out of equilibrium chiral magnetic effect. I didn't discuss it at all. And I briefly mentioned the precise Wigner-Weyl calculus for lattice models. And this is again the list of my collaborators and the general list of papers, main papers on which I base my report. So thank you for listening. Well, thank you. That's all.
Yeah, thank you very much. So the question to the audience, do we have questions? If no question, I have a short question, maybe not specifically related, but just is there any kind of boson fermionic correspondence in the which would help compute some invariance in this particular subject?
I didn't study this. I understand that you suppose that maybe using this correspondence we can develop analytical methods for calculation of this.
Yes.
I really don't know. I really don't know. I
Because
only know. Yeah, I see.
yeah.
But I only know that this guy is given by this quantity from non-commutative geometry developed by Kohn and co-authors. And but I also haven't seen the papers, the practical calculations of these invariants. So what is missing here is a real calculation of invariant by mathematician. This is what I'm looking for. I'm looking for a mathematician who will help me to develop methods for the calculation of this invariant, which is for the physicist, this invariant, especially for the non-homogeneous cases, complicated because even the simplest algebraic topology is far from us. And this is the next step already after the ordinary algebraic topology. This is non-computative geometry with cyclic cohomology theory and all that stuff. So this is a deep mathematical issue which may be explored only by mathematicians, I suppose.
Yeah, I see. Thank you. So any other questions? So if there is no questions, let us thank the speaker today. Thank you very much, Michel.
Okay.
For a very interesting talk. Very instructive in certain points. Yes. Thank you.
Okay. Thank you.